Hi there, I'm Mr. Orr, and today we are looking in your algebra textbooks at section 6.4, which is the combination or elimination method of solving two linear equations simultaneously. Now, combination and elimination are just two different words that refer to the same process. You may recall, up until this point, we have solved linear equations, two linear equations simultaneously to find the point of intersection with two different methods. We used the graphing method, but we decided that that's not always accurate because you can't always tell where the two lines are intersecting, even if you do your best to make the lines as accurate as possible. The second method we used, which is perfectly accurate, is the substitution method. And that's where you set one of the equations equal to a variable, and then you take what that variable is equal to and substitute it into the other equation. We've reviewed that in a previous video, so I won't go back over that now. The third method is also very useful, and that is this combination or elimination, and I'll show you how it works. Here are two linear equations, and we want to find out the point of intersection of these two. Now, in this particular case, you'll notice that neither one is set up particularly well for the substitution method, although I could go through and divide this one by 3 and then isolate the y. So I could use substitution here. It wouldn't be too hard, but let's do this. Take this equation and write it underneath the first one, equals 12. And I'm going to now add the two equations together. So I'm going to do 7x plus 6x is 13x. 3y plus negative 3y is no y's at all, they cancel out, equals, and I get 27 plus 12 is 39. I divide by 13, and I get x equals 3. Once I have that, I can take it into either one of the two originals. Let's put it over here. 3 times 6 is 18, minus 3y equals 12. I subtract 18, and I get negative 3y equals negative 6, or y equals 2. So the point of intersection of these two is 3, 2. And if you went back and checked, you should discover that that works in both equations. That is to say, this side will equal this side, and this side will equal this side if you substitute 3 and 2 for x and y. Point of intersection. Now, I set this one up deliberately to work fairly easily, because as you can see, I had 3y and negative 3y. And when I added them together, I eliminated the y's, and I was then able to solve for x. The idea here is to eliminate one of the two variables when you add the two equations together, so that you end up with an equation in only one variable, which you can then solve, then take the solution and plug it back into one of the two equations in order to find the other variable. All right, so let's try another one, but they're not always set up as conveniently for you. The next one I'm going to do is, let me find one that I rather, okay, here's a good one. 5x plus 6y equals negative 8. And the other one is 2x plus 3y equals negative 5. Now, these are not set up. This is a 6 here. Let me just fix that. And that's a y. All right. These are not set up for conveniently putting one underneath the other and adding them, because I would get 7x and I would get 9y, and that doesn't help me because I have to eliminate one of the variables. So here's what we're going to do. Notice that 6 is twice 3. So if I take this entire equation and multiply every term by negative 2, I'm going to get a negative 6y, this times this, which will cancel out with my positive 6y. So when I do this, multiply by negative 2, I get negative 4x minus 6y equals 10. Now, this is adding these two equations together. 5x plus negative 4x is x. Those cancel. Equals negative 10. Negative 8 plus 10 is 2. X equals 2. All right, take that value, put it back in here. I get 2 times 2 is 4, plus 3y equals negative 5, minus 4. I get 3y equals negative 9, or y equals negative 3. So the point of intersection is 2, negative 3. All right? Now, let's look at another one that requires even more work. Let's take a look at one where neither of the equations is set up conveniently. And by the way, it's always a good idea to get in the habit of putting them into standard form before you do this, just to be consistent so that you have your x's lined up with your x's, your y's with your y's, and your constants with your constants on the other side. All right, let's take 4x plus 2y equals 8. Let me make sure this one actually works well. I believe it does. Yes. Okay, 4x plus 2y equals 8. And the other equation is 3x plus 3y equals 9. Now, in this case, we don't have the same number of x's and we don't have the same number of y's. We also are going to have to do something to both equations because 3 and 4 are not, one is not a multiple of the other, and 2 and 3, one is not a multiple of the other. So what I'm going to do is multiply this equation, let's multiply this equation by 3, and multiply this equation over here by negative 2. All right? Now, what I get when I do that over here is 12x plus 6y equals 24, and I get negative 6x minus 6y equals negative 18. Now I have what I want because the y's will cancel. By the way, it doesn't matter whether you cancel the x's or the y's, whatever is most convenient. So now I get 12x plus negative 6x is 6x. Those cancel. Equals 24 minus 18 is 6, so x equals 1. Now take that value, x equals 1, put it in here. I get 3 plus 3y equals 9 minus 3. I get 3y equals 6, or y equals 2. So my point of intersection is 1, 2. And that's the more complicated version where you have to multiply each equation by a different number. It's okay to multiply each equation by a different number as long as you multiply all the terms in this equation by the same number and all the terms in this equation by this same number. Okay? Now, I believe that's probably sufficient for these problems. So I think we'll leave this video at that and close it out for now. Thank you very much. I'll see you later.